Ever feel like the universe is a giant, complicated mystery? Well, what if I told you that you could understand its basic rules without needing a PhD? Welcome to Theoretical Physics for Dummies, where we'll unravel the secrets of the cosmos in a way that is easy and fun. Theoretical physics isn't just for geniuses in labs. It's a way of thinking, a grand adventure for your mind. It's about asking the biggest questions. Where did we come from? What is reality? And what are the fundamental laws governing everything? Think of the universe as having a giant rulebook. Theoretical physicists are the detectives trying to read it, piecing together clues to understand how it all works. They use the power of mathematics and, most importantly, imagination to propose ideas about how reality functions long before we can even test them with experiments. So what exactly is this theoretical physics? At its core, it's about creating models of reality. Imagine you're a detective trying to solve a cosmic mystery. You don't have all the evidence yet, but you can use logic and what you already know to build a theory about what might have happened. That's what theoretical physicists do. They use math as their magnifying glass and their imagination as their flashlight, exploring the dark corners of the universe. They build theories that can then be tested by experimental physicists. It's this beautiful dance between theory and experiment that drives science forward. From the tiniest particles to the vastness of space, these theories are our best attempt to write the story of our universe. Let's start our journey with something familiar, classical mechanics, also known as Newtonian physics. This is the physics of our everyday world, figured out by Sir Isaac Newton hundreds of years ago. It's pretty intuitive. An object at rest stays at rest, and an object in motion stays in motion unless something pushes or pulls it. Simple, right? This is the concept of inertia. Newton also gave us the famous equation, F equals ma, which means force equals mass times acceleration. In simple terms, the harder you push something, the faster it accelerates. And the heavier it is, the more force you need to get it moving. He also described gravity as an invisible hand pulling things together. That's why an apple falls from a tree and why the moon orbits the Earth. For centuries, these laws seemed to explain everything perfectly. But then, at the turn of the 20th century, a young patent clerk named Albert Einstein came along and completely turned our understanding of the universe upside down. He realized that Newton's laws weren't the whole story, especially when things move very, very fast. He introduced us to the theory of relativity. Einstein's big idea was that space and time are not separate things. They are woven together into a single, four-dimensional fabric called spacetime. And what we perceive as gravity isn't a force pulling us down, but rather the curvature of this space-time fabric. Imagine placing a bowling ball on a trampoline. It creates a dip, and a marble rolled nearby will circle around it. That's what massive objects like the sun do to space-time, and the Earth is just rolling along that curve. One of the wildest consequences of this is time dilation. The faster you move through space, the slower you move through time relative to a stationary observer. Yes, time travel into the future is theoretically possible. Just when physicists thought they were getting a handle on the big stuff, they looked at the world of the very, very small and things got even weirder. Welcome to quantum mechanics. At this subatomic level, the neat, predictable rules of the classical world break down completely. Particles like electrons don't just behave like tiny balls. They can also act like waves spread out in space. This is called wave-particle duality. Then there's the Heisenberg uncertainty principle, which states that you can know both the exact position and the exact momentum of a particle at the same time. The more precisely you measure one, the less you know about the other. It's a fundamental limit on our knowledge of the universe. Perhaps the most famous concept is superposition, often explained with the thought experiment of Schrödinger's cat. A cat in a box is both alive and dead at the same time until we open the box and observe it. This isn't just a quirky idea. It describes how particles exist in a cloud of possibilities until they are measured. So what is everything in the universe actually made of? This is the domain of particle physics. If you could zoom in on anything in your hand, the air, a star, you'd find that it is all made from a surprisingly small set of fundamental particles. Think of it like the universe's ultimate Lego set. These particles are the building blocks of matter, and they include quarks, which make up protons and neutrons and leptons, like the familiar electron. But it's not just about the blocks, it's also about how they stick together. That's where the fundamental forces come in. There are four of them: gravity, which we've talked about; electromagnetism, which holds atoms together and is responsible for light; the strong nuclear force, which binds atomic nuclei; and the weak nuclear force, which is responsible for radioactive decay. Everything you see and experience is just a complex dance of these few particles and forces. Now let's zoom all the way out and look at the universe as a whole. This is the field of cosmology. The reigning theory for the origin of our universe is the Big Bang. About 13.8 billion years ago, all the matter and energy in the universe was concentrated into an incredibly hot, dense point. Then it exploded and has been expanding and cooling ever since. A great way to visualize this is to imagine a loaf of raisin bread dough rising in an oven. As the dough expands, all the raisins move farther apart from each other, but they aren't moving through the dough. The dough itself is expanding. Similarly, galaxies aren't flying through space. Space itself is stretching, carrying the galaxies with it. But as we looked closer, we found a mystery. The universe is expanding faster than it should be. To explain this, scientists propose the existence of dark energy, a mysterious force pushing everything apart. We also found that galaxies are spinning too fast to hold themselves together with the gravity from visible matter alone. This led to the idea of dark matter, an invisible substance that provides the extra gravitational glue. Together, dark matter and dark energy make up about 95% of the universe. We can only see the remaining 5%. So where do we go from here? The frontiers of theoretical physics are buzzing with mind-bending ideas. The ultimate goal for many physicists is to find a theory of everything, a single, elegant equation or framework that can unite all the forces of nature, combining Einstein's relativity for the very large with quantum mechanics for the very small. One of the most famous and controversial candidates for this is string theory. It proposes that at the most fundamental level, all particles are not points but tiny, vibrating one-dimensional strings. Different vibrations of these strings give rise to different particles, like different notes on a violin string create different sounds. String theory also predicts the existence of extra dimensions beyond the 3 of space and 1 of time that we know. These ideas also open up the possibility of a multiverse and infinite collection of parallel universes, each with potentially different laws of physics. We are truly living in a golden age of cosmic exploration, even if much of it is happening on blackboards and in the minds of theorists. The universe is a vast and incredible place, and we've only just scratched the surface. But hopefully, you now have a better sense of the big ideas that physicists used to try and understand it all. From Newton's apples to Einstein's spacetime, from quantum weirdness to vibrating strings, the story of physics is a testament to human curiosity. Science isn't a destination, it's a journey of constant discovery. Never stop asking questions, never stop wondering, and never stop learning. The universe is waiting to be explored. If you enjoyed this journey through the cosmos, make sure to hit that like button and subscribe for more adventures into the world of science. Thanks for watching, and keep looking up.